My dear students, now we are going to look at 3-bit asynchronous down counter. We will be trying to design it and we will go through the steps. As you are aware of whatever we are going to do a design, okay, with respect to asynchronous or synchronous counters, what we need to do is we need to find number one step, number of flip-flops required. Step number one. So the number of flip-flops required is very simple in this case, right? What exactly the number of flip-flops required? Number of flip-flops required are equal to number of bits. Say 3 bit. So 3 flip-flops. What we need is a down counter, of course. So we will choose under step 2 we will choose the flip-flops. Now we can choose if you want JK or T or D or SR, whatever you want. So let us fix ourselves to T flip-flop as of now. Okay. Next, what is required for us is state diagram. Step 3. We know what is this step. In this step 3, what exactly we are going to do. In step 2, then step 3. So in the step 2, we have decided to use T flip-flop. In step 3, state diagram. Very simple, right? State diagram. So it will be from state 7 to state 6, 6 to 5, 5 to 4, then 4 to 3, 3 to 2, 2 to 1, 1 to 1 to 0, then 0 to 7. And this also I can show in a circle just to make this process simple. Okay, state diagram. Next step what we try to do is we look at truth table. What is truth table? Truth table, input output relations. What is input output relation? What is input in the circuits? Input in asynchronous counters is clock. What is the output? Output is count value. Output is count value. Go on changing. Count value. Initially it will be 7, then 6, then 5, then 4. So count value. What is count value? Contents of flip-flops. Contents of flip-flops. What is there in the flip-flop? Initially flip-flops containing 7, then it will become 6, then it will become 5. Likewise it will go up to 0. It is called 3-bit down counter. That's all right. So always input to the asynchronous counter is clock. Output is count value. From where you will get output? Output is flip-flop outputs. Let's say ABC flip-flops if at all we are using. Okay. QA, QB, QC states of the flip-flops. What is QA? QA is LSB. LSB. What is QC? Is MSB. So where do we apply clock? Always will apply clock to LSB. LSB flip-flop. I mean to say clock is applied to LSB flip-flop. Okay. Next, what we try to do is there should be some reset logic. Reset logic is required only for a logic is required. This is optional. Reset logic. What is reset logic? Logic is when it is going to terminate the count. Here we are not terminating any count. Okay. So we are not going to do any reset logic. Okay. Then what we try to do? We draw the circuit diagram. We draw. So this is step number 5. Step 5 is reset logic. Step 6, what we try to do is we try to draw the circuit diagram. Draw circuit diagram. Once circuit diagram is available, now what we can do? We can analyze the circuit with respect to the clock and we can go for timing diagram. So from the timing diagram, what I try to show you that it is a down counter. So what exactly we can do is we can go for timing diagram. Okay. So this is all the things. So what we try to do is we need three flip-flops. So how this flip-flop should be? The free flip-flop should be in toggle mode. What is toggle mode? Means every time when the clock comes, it has to change its value. Then only it is possible to get a counter value. So what I try to do is I use flip-flop A, flip-flop B, flip-flop C. There is Q and Q bar. There is a Q and Q bar. There is a Q bar and Q. So this is your QA. This is your QA. There will be QB. This is your Q. There will be QC. This is your QC. There is a clock input to the flip flop. There is an input TA. This input T is called TA. This TA is logic 1. There is an input to flip flop B, which is called as TB, which is 1. There is an input to T, which is TC, which is connected to 1. Now output of this flip flop is input to the next flip flop. Output of this flip flop is input to the next flip flop. If I connect like this, okay, what I am going to get is, okay, if I connect like this, initially when clock is not yet applied, okay, initially all the flip flops are zeros. So this is 0, this is 0, this is 0. Now when you apply the clock, it toggles. This one toggles. That toggle is applied to the next flip flop. That toggle is applied to the next flip flop. So what I mean to say is output is changing. The changing clock is applied to here, and this is also toggles. This is applied to the next. That is also toggles. So initially it is 0, 0, 0. If I do the toggling, there is every possibility that from 0, 0, 0, 0, I go to some state, okay, where it may be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, so on and so forth. I can go up to 1, 1. So that will give you up count. So, but I don't want up count. I want down count. So, what for that, what I try to do is, instead of connecting to Q, I'll connect it to Q bar. What I do is, I'll connect it to Q bar. Initially, this content is 0. That means by default it is 1. Q bar, right? So what I try to do is, I'll connect from here and I'll connect it to this. So the clock input for the flip-flop B is QA bar. For clock input to the flip-flop C is QB bar. Okay. So if I do that and if I try to analyze the circuit, now I will get the down counting. So by default, when all flip-flops are ones, okay. Now what you are trying to do? Well, all are, say you are what exactly you are trying to do. What exactly that we are trying to do is we are trying to look at, okay, Q A bar, QB bar and QC bar. Okay. So this is your QC, this is your QC bar, of course. Now earlier what we were doing in up counter, we would like to take the output from QA, QB, QC. Now we don't want output from QA, QB, QC because we want down count. So we will take QA bar, QB bar and QC bar. Okay. So if you take them and if you try to see, okay, we will get that it is going to have a down counting. Okay. How to analyze that? It's very simple. You take the clock, you look at QA, you look at QA bar, then you work it out. Okay. So that's we will do it now, of course. So what I try to do is, let us make an analysis. Let's suppose there is a clock is applied. So clock is running like this. When clock is running like this, What sort of clock input we have for our flip-flop? Active low logic. What is active low logic? There is a bubble wherever you are applying the clock. So that means it will be active when it is going from 1 to 0. So 1 to 0, 1 to 0, 1 to 0, 1 to 0, 1 to 0 is the reference. Okay. So then 1 to 0 is the reference. This is what exactly known as clock. Okay. Now initially, what is the initial value of QA bar? We are interested in QA bar. QA bar is 1. Now what is going to happen? During this edge it will going to 0 because it toggles. Every time it's going to change, toggles. So it toggles here, it toggles here, it toggles here. Wherever the negative is there, it is going to toggle. So 1, this becomes 0. Sorry, initially it is 1, right? So when it toggles means it goes down. Goes down means it has to be 0. So the drawing should be not proper. Okay. So let's make the drawing properly. That is initially QA bar is 1 till here. Now it goes low during this pulse for the next trigger. For the next trigger it will be 1. For the next trigger it will be 0. For the next trigger it will be 1. For the next trigger it will be 0. For next trigger it will be 1. For the next trigger it will be 0. Okay. So what I try to do is initially it is 1, then it has become 0, 1, 0, 1, 0. Okay. Then 1, next will be 0. So if you want to extend, you can extend this till the next edge. This is 0. Now what about QB bar? QB bar, if at all you see, it is 1 because where is the negative? Where is exactly the negative edge is happening? So if you look at it here for QB bar, right? So initially, what is happening? Initially it is 1. QB bar is also 1. So what is happening is this is changing, right? So this is 1 during the negative clock edge. What is happening is it's going to low, and it will be low for up to here. Then what exactly it is going to happen? This is high, then it is low, then it is high. Okay, it continues, right? So what exactly that we are trying to do is we will look at these values 1 0 0 1 1 0 0 1, then okay. Now what exactly QC bar? QC bar is also initially 1. Now this is the input to whom? This is the input to QC. So this is input to flip-flop C. So during this, what exactly happens is it goes low. It goes low, then it will be low for next till the next stage. Then it will be high further for the next block. So this is initially 1, this is 0, this is 0, this is 0, this is 0, this is 1, this is 1, this is 1. So what we try to do is we try to collect the values of QA bar, QB bar and QC bar. QA bar, QB bar and QC bar. When I collect here it is 1 1 1. When I collect here it is 0 0 0. When I collect here 0 0 1. When I collect here 0 1 0. When I collect here 0 1 1. When I collect here it is 0 0 1. When I collect here 101. When I collect here, 011. When I collect here, this is 1, right? 111. I have started with 111. I have ended with 1. Now it will repeat the sequence. So this is nothing but counting down, right? So this is how, simply by connecting QA bar, QB bar and QC bar to the next flip-flop clock signals. QA bar as a clock input to QB bar, flip-flop B. Then QB bar is input to the clock input to the flip-flop C. That will give you, okay. So this is how exactly I can get 3-bit asynchronous down counter. So exactly it is easy and possible. You can analyze with 4-bit asynchronous counter possible, 5-bit possible, like the way that we have discussed with respect to 3-bit. Okay, so rest all will be same. So this is what exactly the design process and analysis, of course, how exactly we are going to get the counting sequence. If you want the counting sequence to stop in between, you can stop in between. Wherever you want, you can stop it. Okay, so that we will see in the due course of time.